let's say we are operating in 3 dimensions, and I have a function rho, which is a function of x, y, or z, and it gives us the mass density at any point in 3 dimensions of some fluid, some particular fluid. Maybe it's a gas or fluid, water, who knows what it is. Some type of substance. It gives us the mass density at any point in 3 dimensions. And let's say we have another function. This is a scalar function. It just gives us a number for any point in 3D. And then let's say we have another function v, which is a vector function. It gives us a vector for any point in 3 dimensions. And this right over here tells us the velocity of that same fluid or gas or whatever we're talking about. Now let's imagine another function. And this might all look a little bit familiar because we went through a very similar exercise in 2 dimensions when we talked about line integrals. Now we're just extending it to 3 dimensions. Let's say we have a function f. And it is equal to the product of rho and v. So for any point in x, y, z, this will give us a vector, and then we'll multiply it times this scalar right over here for that same point in 3 dimensions. So it's equal to rho times v, times v. Let me use that same color that I used for v before. Rho times v. And there's a couple of ways you could conceptualize this. You could view this as it obviously maintains the direction of the velocity, but now its magnitude, one way to think about it is kind of the momentum density. If that doesn't make too much sense, you don't have to worry too much about it. Hopefully, as we use these 2 functions and we think a little bit more about them relative to a surface, it'll make a little bit more conceptual sense. Now, what I want to do is think about what it means given this function f to evaluate the surface integral over some surface. So we're going to evaluate over some surface. We're going to evaluate f. Dot n, where n is the unit normal vector at each point on that surface, ds, d capital S, d surface. So let's think about what this is saying. So first let me draw my axes. So I have my z-axis. This could be my, let's make that my x-axis. And let's say that this right over here is my y-axis. And let's say my surface, I'll use that same color, my surface looks something like that. So that is my surface. That is the surface in question. That is S. Now let's think about the units, and hopefully that'll give us conceptual understanding of what this thing right over here is measuring. It's completely analogous to what we did in the 2-dimensional case with line integrals. So we have a ds. A ds is a little chunk of area of that surface. So that is ds. So this is going to be area. And if we want to pick particular units, this could be square. This could be square meters. And I think when you do particular units, it starts to make a little bit more concrete sense. Now, the normal vector at that ds, the normal vector is going to point right out of it. It's literally normal to that plane. It has a magnitude 1. So that is our unit normal vector. And f is defined throughout this 3-dimensional space. You give me any x, y, z, I'll know its mass density, I'll know its velocity, and I'll get some f. At any point in 3-dimensional space, including on this surface, including right over here. So right over here, f might look something like this. So that is f right at that point. So what does all this mean? Well, when you take the dot product of 2 vectors, it's essentially saying how much do they go together. And since n is a unit vector, since it has a magnitude 1, this is essentially saying what is the magnitude of the component of f that's going in the direction of n? Or what is the magnitude of the component of f that is normal to the surface? Or how much of f is normal to the surface? So the component of f that is normal to the surface might look something like that. And this right over here will essentially just give the magnitude of that. And it's just going to keep the units of f. And right over here just specifies the direction. It has no units associated with it. It's dimensionless. F's units are going to be units of mass density. So it's going to be, let's say it could be kilogram per meter cubed. That's actually just the rho part. So it's mass density times velocity times meters per second. Let me write in those colors just so we have clear what's happening here. So the units of f are going to be the units of rho, which are going to be kilogram per cubic meter, that's mass density, times the units of V, which is meters per second, and we're going to multiply that times meters squared. So what you have is you have a meter and then a meter squared in the numerator. That's meters cubed in the numerator, and meters cubed in the denominator. That cancels out. And so the units that we get for this, are kilogram per second. And so the way to conceptualize it, given how we've defined F, or what we say F represents, the way to conceptualize this is saying how much mass, given this mass density, this velocity, is going directly out of this little ds, this little infinitesimally chunk of surface in a given amount of time. And then if we were to add up all the ds's, and this is what essentially that surface integral is, we're essentially saying how much mass in kilograms per second, that's what we picked, how much mass is traveling across this surface at any given moment in time. And this is really the same idea we do with the line integrals. This is essentially the flux through a two-dimensional surface. So this is the flux through a 2D surface, through a 2D surface. And this isn't like some crazy abstract thing. I mean, you could imagine something like water vapor in your bathroom. And I like to imagine that because that's actually visible, especially when sunlight is shining through it. And we've all seen water vapor in our bathroom when you have a ray of sunlight, and you can see how the particles are traveling, and you see they have a certain density at different points. And so you can imagine you care about the surface of your, maybe you have a window. Maybe you have a window in the bathroom. So you have a window. And so if the surface was the window, and let's say the window is open, so it's kind of there's nothing physical there, it's just kind of a rectangular surface that things can pass freely through. And F was essentially the mass density of the water vapor times the velocity of the water vapor, then this thing right over here will essentially tell you the mass of water vapor that is traveling through that window at any given moment of time. Another way to think about it is imagine a river, and I'm going to conceptualize this river as kind of just a section of the river. And I'm conceptualizing it, this is kind of a river. Obviously, this would be the surface that we normally see, but obviously it has some depth. It's three-dimensional in nature. And so we would know the density. Maybe it's constant. You know the density and you know the velocity at any point. That's what F gives us. So that tells us, as we said, we could view that as the momentum density at any given point in time. And maybe our surface is some type of a net. And the net doesn't even have to be rectangular. It could be some weird shaped net, but I'll do it rectangular just because it's easy to draw. It's some type of net that in no way impedes the flow of the fluid. Then once again, when you evaluate this integral, it will tell you the mass of fluid that is flowing through that net at any given moment of time. So hopefully this makes a little bit of conceptual sense now. In the next few videos, we'll actually think about how to calculate this and how we can actually represent it in different ways.